Everyone, welcome to your play posit for the week. It's perfect timing because I only have about 8 slides that I was going to go through with you guys today on this play posit. So we're going to use a little bit of our time together today to finish up our notes from class this week on Wednesday. So go ahead and grab your notes from December 8th, our Wednesday class, and we are going to finish those right now. So now let's get into more of the different kinds of quadrilaterals you guys are going to see. You're going to see some rectangles, rhombi, and squares. So here's some examples of those in real life. These are some rings, some square-shaped rings. I don't know how comfortable those would be. Gosh, I don't know. A rectangular pool and a rhombus sculpture in a park. All right, so if you remember, we looked at this chart in the class last time together, and I just want to make sure you guys have the different properties of the shapes marked down. So you might want to pause and go ahead and make sure that you have the X's in the right spot. So in a rectangle, both pairs of opposite sides are parallel. This should say parallel. So we can mark our picture up here to show that with the arrows. And let's see, the next one is diagonals are congruent. And they bisect each other. So this is what we talked about in that last slide. Bisect meaning two equal parts. But they're also congruent. So, you know, this one equals this one. They are equal. Both pairs of opposite angles congruent, and we know that they're all 90, right? In a rectangle. Both pairs of opposite angles are congruent, opposite sides congruent. Oh, that's what it was. This one and this one, this one. Look how marked up it's getting. It almost looks like a design of some sort. All angles are equal. We show that with our 90-degree angle marker there. Adjacent angles are supplementary. So this is what we were talking about over here. These adjacent angles or consecutive angles, same thing, are supplementary. So 90 plus 90 is 180, so that is true. So let's do an example with a rectangle. It wants us to find all this stuff. So let's find X first. So we know that the diagonals bisect each other, so that means this piece equals this piece. And that's going to help us because here's the X. So if we know they're equal, then let's set them equal. And we can solve for X, right? This is 5 times X, so we'll just divide both sides by 5. And so X equals 3. There we go. The next one is angle BCA. BCA. So we're looking for this angle right here. Now this is where it comes into play where we talk about the whole transversal parallel line business. So because you have these diagonals here, we know this is going to be 37. And the other way we know this is actually because of the fact that these are congruent triangles. Because these two sides, all of these, look, it's congruent by side, side, side. Remember those postulates? Side, 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 side. So that means this angle, this triangle down here and this triangle up here, they're all going to have corresponding parts that are the same. So that'll make this 37 and this 37. So that's helping us out. We're kind of working our way through the picture. The other thing we know about these angles here is that they add up to 90 degrees, right? We know that the angle here is 90. So if this part's 37, then that means this part is going to be 90 minus 37, which is 53. So BCA is 53 degrees. All right, C, measure of BRA. Well, if you know these two angle measures, you can find the third, right? We know that all the angles in a triangle add up to 180. So to find BRA, we could just do 180 minus the other two angles. and that is 106 degrees. All right, so this is 106. You can see our picture starts to get quite full, so sometimes people like to redraw the diagram for each one of these. It's totally up to you. It helps to use different colors sometimes too. So D says the measure of ARD. ARD, we're looking for this angle right here. There's a few ways to find that. I feel like if you can see that this is 106, check this out. Look, this straight line here, these are two angles right next to each other on a straight line. What do they add up to? 180. So this angle is going to be 180 minus 106. We're using that angle pair relationship, right? It's a pair of angles on a straight line. They are adjacent to each other, so they are supplementary. So that is 74 degrees. And you could definitely check that with your Desmos calculator. All right, last but not least, AC. They want us to find the length of the whole diagonal. Well, that one's easy, right? Because we know this piece is 15. And really, you don't even need to find x because we know that they're equal. So that's 15, and this is 15 also, which we know it is because 5 times 3 is 15. So the whole thing would be 15 plus 15, which is 30. 30 units. Whatever the units might be. We don't know if it's inches, centimeters, feet, miles. All right, so you can see how we're using all the different properties of a rectangle to sort of work ourselves through the picture and find the missing values. And we're going to do that for each of the shapes. So here's the rhombus. Again, you want to take a pause. Make sure you have all of these items marked in your diagram for rhombus. The diagonals are perpendicular, which means they form 90-degree angles. The diagonals bisect the opposite angles. That means these are equal to each other. Little pieces here. They also bisect each other like they do in a rectangle. Both pairs of opposite sides are equal. Actually, this should be 3. Look at all the markings. It really does look like a design. It's really cool. Both pairs of opposite angles are congruent. That makes sense because the parts are congruent. And adjacent angles, again, are supplementary. They add up to 180. So let's do one. Find the measure of, or find the value of x. So there they are again on our diagonal. So we know that those parts are equal because the diagonals bisect each other. So let's just set them equal and solve for x. Okay, all the x's together. 2x minus 4 equals 0. And now let's start solving for x. So get x all by itself. I'm hoping you guys feel like this part is super easy. And if not, that is okay. You can definitely, reach out for help or keep practicing solving those equations. Good to know we did a lot of it last year in Algebra 1. So I'm hoping it's coming back to you. Excuse me, big yawn. And it's not even late. I don't know what's happening. X equals 2. All right, let's find B. B says, find the measure of OCD. OCD. So we're looking for this angle right here. And this is very similar to what we did in that last diagram where we used the idea of that the triangles are congruent. So all the parts are congruent. And we know they're congruent because of the fact that all these side lengths are equal, right? So we know that the triangles are congruent, and which means all the parts are by side, side, side postulate. All right, so let's find B. B is OCD. So actually, we are looking for, this angle, right? O to C to D. So here, to find the measure of this angle, since we know this is 28, this is also 28. And it can be kind of hard to see with all the markings going on. So let me try to... So what we have here are some alternate interior angles. Those alternate across that transversal. In this case, it's a diagonal is the transversal, and here are the parallel lines. So remember, we have those alternate interior angles, and they are congruent. All right, now let's find AOB. AOB is right here in the middle, AOB. And actually, we know that all of the angle measures on the inside are 90 degrees. And how do we know that? And that's because, I don't want to go back too far. Oh, here we go. That's because the diagonals, let's see, where is it on here? Ah, here it is. Diagonals are perpendicular. So because they are perpendicular, we know perpendicular lines form those 90-degree angles. So we instantly know that AOB is 90 degrees. All right, let's find the length of OB. OB is just this piece of that diagonal. So we found x to be 2, so we could just plug 2 in for x. And the length is 8 units long. Part E says to find AB. So when you're looking at AB, all we know is that this is 8 and this is 8. That's it. We only know one side length. So right now, we don't really have enough information. We don't. There's not enough information to solve this. This is a right angle. We could talk about using the Pythagorean theorem, but we only know one side length. When we get to the end of semester 2, when we talk about trig, we could potentially use some trig functions to find this length AB. Yeah, we could definitely do that. But right now, we don't know, so we're going to say not enough information. And lastly, the measure of angle ADO. ADO is up here. Let me get a different color. There we go. And we're going to use the properties of congruent triangles. The side postulate tells us that all the corresponding parts are congruent. Remember that CP, CTC business. So because so let's work through some of this. This is 28, this is 90. So we can find this third angle, right? 90, or we do 180 minus 90 minus 28, and we would get 62 down here. And then because of the same reason we found the 28, we know this is 62, that alternating interior angle business. Now look, we know that these angles, excuse me, sorry, they are sort of consecutive, not really, I don't want to say consecutive, but they are a pair, they're right next to each other. So let's see if we can keep working through this. We know that these triangles are congruent and the two triangles on the sides are congruent. So that must mean this is 62 and this is 28. Excuse me. This is 28 and this is 62. So you kind of just work your way through the picture using that side postulate to match up the side length. Because look, the 2 tick mark is across from the 62 here, and so it's got to be across from the 62 here. So ADO is 62. All right, here's our properties of a square. Make sure you have all of the appropriate ones marked. You guys can hit pause. I'm hesitant to mark up this diagram because sometimes I think it just makes it look confusing, but we can. It's very artistic. Both pairs of opposite sides are parallel. Maybe I can use different colors. Let's see what happens there. The diagonals are perpendicular, which means that they form those right angles there. Here's a new one. The diagonals bisect the angles. So that means They bisect each other, but they also bisect the angle. So this is going to equal this. These two pieces are going to be equal, these two little angles. So not only do the pieces bisect, so do the angles. We haven't seen that yet. Diagonals are also congruent. The whole thing is congruent to the other whole thing. What else? Both pairs of opposite sides are equal, a different color. And we know this is a square, so they're actually all equal. We could do that if we wanted to. We can make those match. What else? Both pairs of opposite angles are congruent, and we know that they are 90 degrees in a square, right? All angles are equal, and adjacent angles are supplementary. So this one plus this one equals 180, which we know because, again, all the angles are 90. Squares are kind of nice like that. So let's try one. Let's find the value of x. So we have our diagonal here. We know that these parts are equal. So let's just go ahead and set them equal. We can solve for x. Subtract 3 from both sides and add 12. We're kind of doing 2 steps in one here. So we get 2x equals 24. Hold on, let me double check this. Oh, I think I wrote 12. Look, it's a 2. I'm glad I caught that before I went too far. So 2 plus 12 is 14. There we go. And we'll divide both sides by 2, and x equals 7. So we got 7 for x, and then we're going to do the same thing to solve for y. And of course, I'm going to run out of room. Of course. So we'll set those two equal, because these are the two side lengths. You know, this b should really be here. It looks like that got pushed over a little. And we'll solve for y. I'm going to subtract 3y from both sides and add 7. So y is 9. 4 minus 3 is 1. Perfect. Here we go. We're going to find the measure of BAD. BAD. So that's this angle right here. We know that squares form 90-degree angles. So that one was easy. Part D says find the measure of angle ABE. So that's this angle here. And because of the properties of a square, we know that the diagonal bisects the angle. So that means it cuts it into 2 equal angles. And half of 90 is 45. So that must be 45. These are going to form 45, 45, 90 triangles. Very special triangles. Part E says DEC. DEC. So we know that the diagonals are perpendicular, which means all of these are 90-degree angles. All right, let's find BE. BE is just this little piece of that diagonal. So it's 3x plus 2. But we found x to be 7. So we'll put in the 7 for x. So you get 21 plus 2, which is 23 units. Yeah. All right. AC is this diagonal. We know that the diagonals are congruent. So if we can find this one, then we know this one. And the reason we're going to find DB is because those are the ones that have the markings on them, the measurements. And we know that it's 23, this piece. So this piece must be 23. So the whole thing is 46 units. And the diagonals are congruent. So we found this one to be 46. So that means this one is also 46. And lastly, the perimeter. So remember, the perimeter is all the way around the outside of the shape. So let's find the length of the side. We know that y is 9, so we can plug in 9. And you get 36 minus 7. Let's see, what is that? That is 29, right? 29 units. So there's 4 sides, so we would need to add up 29 4 times. 116 units. Is that right? 4 times 29. I'm always afraid I'm gonna in a recording. It happens. 116. All right. Perfect. Okay, so hopefully by now you're seeing that these shapes are all pretty similar, especially in the methods that we use to solve them. Let's move to the trapezoid and press pause. And here are the, oh, that one got cut off a little bit. Let me grab that for you. Hold on. Okay, there we go. So now I have the full, you can see here I have the full chart in here, but they're still not marked. The only thing that's special about a trapezoid is exactly one pair of opposite sides are parallel. You can see it's this pair right here. Obviously, the two on the left and the right are not parallel, but that's it. There's a special kind of trapezoid called an isosceles trapezoid, and that one has a lot more going on, and we're going to talk about that one next. All right, so given this trapezoid, we're going to find all these things over here. So find the measure, or find the length of x. So one thing we didn't talk about on the last slide, which maybe we should, let's just go back to that, is a trapezoid has something that goes right through the middle here called a mid-segment. The nice thing about it is the name matches what it is. It cuts the shape down the middle, essentially, on each side. So what that means is that this piece ends up being equal to this piece. Not so much over here because that's not a straight line. The other thing that's super special is that, actually this does cut this in half, so these should be equal. But the other thing that's really cool is this now becomes like a transversal here. So that would mean this angle is equal to this angle, and all of those special properties start to come into play. If you want to find the length of the mid-segment, we can start labeling this like base 1 and base 2. All you do is you add the bases together and divide by 2. That gives you the average between them. So we're going to add base 1 plus base 2, and it'll give you that middle length. So let's do that. We know that these are equal. So to find x, we'll say 8 equals 4x. So x is 2. That was easy. EF, they want us to find the mid-segment now. All right, so 33 divided by 2, that's, let's see, that's decimal for sure, 16 something, 16.5. So we could write 16.5 if we wanted to. 16.5 units. All right, CDA, that's this angle down here. And like I said before, these are corresponding angles, so this is also going to be 84 degrees. D is BEF. So using those same properties of parallel lines and transversals, these are consecutive, same side interior. So they are going to add up to 180 degrees. So that means this is 180 minus 104. It's going to be 76 degrees right here. Last one is BCD. So same idea. Careful, these are not congruent necessarily. Let's figure out the same side interior or consecutive interior. So 180 minus 84. That's going to be 96. All right, our very last shape of the day, this is an isosceles trapezoid. So remember, an isosceles triangle has 2 equal sides. So the same idea with an isosceles trapezoid is that those sides are going to be equal, like in a triangle. You know, you can kind of imagine this being extended to form that isosceles triangle. It's an isosceles trapezoid. So all of these properties are marked. One pair of opposite sides are parallel, exactly one pair, not 2, so it's going to be this pair, right? They're parallel. The diagonals are congruent. The diagonals bisect each other. Exactly one pair of opposite sides are congruent. It's this pair, right? Because this base up top is much longer than the bottom. And lastly, base angles are congruent. So base angles are congruent. So let's look at an example. The figure shows an isosceles trapezoid, so it's important that they told you that. So let's label what we have. FK is 9, and JG is 26. Find KH. So we know that the entire length of this diagonal is 26. So that means this whole thing is 26 because they're congruent. So to find this little piece, we just need to do 26 minus 9. Just to be sure, yep, 26 minus 9, 17. 17 units. I know this one was a lot shorter than the other ones that we've done, but I just wanted to. So let's get to our slides for the day. So this is going to be the 12-9 notes in your OMHS. So let's recall what similar shapes are. I'm going to grab my pen tool. Similar shapes are the same shape, but different size, potentially, usually. So they're same shape, different size. The symbol for similar is just the one tilde or the one squiggle. We've seen this one. This means congruent, right? And that means like they're the exact same shape and the exact same size. But today we're going to talk about similar shapes, things that are the same shape but different sizes. So like here's an example. These are the same shape, they're both triangles, but they're obviously different sizes. Similar shapes have special properties. They have congruent angles and proportional sides. Proportional sides, and we're going to review what proportions are here in a minute. So are these shapes similar? So we do have congruent angle pairs. They all match up. And then in order to sort of test it, we want to set up some ratios and proportions. Remember, a ratio is just a fraction. And a proportion is two fractions set equal to each other, like 1/2 equals 2/4. That's a proportion. So we're just going to match up the parts and set up some proportions. So let's see. Let's do, you can see that this one is sort of flipped over. So we're going to do the small base over the small base, the large base over the large base, the left side over the left side. It's important to keep them in the similar sides of the figure, right? We wouldn't want to do like 28 over 15.5. Those two sides don't match up. And 12.4 over 15.5. Now all we have to do is take our calculator and see what decimal we get when we divide these numbers. So I'm going to grab my calculator. 20 divided by 25 is 0.8. 28 divided by 35 is 0.8. Let's see, I'm guessing this is also 0.8. Yep, 0.8. And these are the same fractions, right? So this will also be 0.8. So see, they have a common ratio, which means those shapes are definitely similar. When the shapes are similar, we can set up these proportions and oftentimes use those to solve for missing lengths. So it's really helpful. Let's see if these shapes are similar. So we could do 8 over 10. They look similar, but let's see. 14 over 21. And then the sides. Let's grab our calculator and see if all of these decimals are the same. Well, we know this is 0.8, right? 14 over 21. Ooh, that is 0.66 repeating. So already you can see that they're not equal. Those ratios are not equal. They're not proportional. So because these are not equal, these are not similar. So we could not use the ratios to help us. So let's just recall how to solve a proportion. There's actually two ways to do this. It's kind of up to you, but when you have two fractions that are set equal to each other like this, remember this whole thing is called a proportion. You can do what's called cross multiplication. So we could do 5 times x equals 7 times 3. Right? We get 5x equals 21, and then we would just divide both sides by 5. Or, remember, you can solve it sort of the traditional way. We could, this is x divided by 3. Remember, the inverse operation of division is multiplication. So we can multiply both sides by 3. And you can see this will still get you 3 times 7 is 21 over 5. You get the same thing. Cross multiplication works a lot better when you have the variable at the bottom. Let's see. 3 times 8 is 24. And 4 times x is 4x. And then we just divide by 4. 6. X is 6. So it's just a handy tool whenever you have two fractions set equal to each other to solve that proportion. So let's use similarity to solve for missing sides. That's the whole big deal with the similarity properties, is we're going to be able to solve for those missing sides. It says use proportions to solve for the missing side. So it does not tell us that the shapes are similar. So I should probably say that up here, the shapes are similar. If we know they're similar, then we know these sides are proportional. So here's a question mark. Let's call that x. We could say x over 24 equals 10 over 15. See, in this case, we're not going to want to use this 15 necessarily because we don't know this side. So you do have to match up those corresponding parts. And now we can cross multiply. 24 times 10 equals x times 15. So 240 equals 15x. That last step to get x by itself, we're just going to divide both sides by 15. And x is 16. And you can definitely check yourself by plugging x in here. We get 16 over 24 equals 10 over 15. Now remember, if they are similar, which we said that they were, these fractions are equal, and sure enough, they are. That's just a nice little check to make sure you did your algebra right here. Let's do another one. We'll call these question marks x. Again, we're going to assume that they are similar. Not assume, I'm telling you they are similar. So x over 25 equals 12 over 15. If you want, you can go the other direction. You could definitely say 25 over x equals 15 over 12. That's totally fine, as long as you're going in the same direction and those corresponding sides. So we're going to have 15x equals 25 times 12, which is 300. And then we'll divide both sides by 15. And x is 20. Let's look at the triangle example. I'm going to go 10 over x equals, now here we know all the sides, so it's up to you. You can pick any side you want. You could do 8 over 4 or 14 over 7. You will get the same answer. So 8x equals 40. And then 40 divided by 8 is 5. Hopefully you're feeling like this is pretty straightforward, pretty easy. Once you set up those fractions, solving that proportion is not too bad. Here are some more. We can continue to try. So we could do 5 over x, equals 6 over 12. So we'll have x times 6 is 6x, 5 times 12 is 60, and divide by 6. X is 10. Be careful with these. Sometimes when they start to change the orientation, see how this one's turned, it can get a little tricky. So if you want, you can return it so it's in the same orientation. Or, you know, here's the slanted side, here's the slanted side. So 54 over 63. Here's the height, if you will, and the height, x over 35. And then you could do 48 over 56. Because you can redraw this if you want, to kind of see the parts that match up. And then we just cross multiply. These are some big numbers. 54 times 35 is 1890, and we'll divide by 63. X is 30. That's nice. All right, here's what I'm calling the challenge. I think this is probably as hard as they're going to get, where you're starting to throw in expressions here, but you solve them the same way. So we'll do 45. Let's see, hold on. Yeah, let's do 45 over 2x plus 4 equals 40 over 16. And we're just going to cross multiply. So 16 times 45 and 40 times 2x plus 4. Make sure that you multiply that 40 by everything. So I had to put this in parentheses. This is 7, I'm going to come up here. This is 720, and then we're going to distribute the 40. 40 times 2 is 80, x, and 40 times 4 is 160. Now we can keep solving, right? Subtract 160 from both sides. $560 equals 80x, and divide by 80. X is 7. Our triangle problem is going to work very similarly. I wish I had more space. You guys, this always happens. I'm going to come up here and try to write very carefully. 63 over 8x minus 2 equals 49 over 42. Those corresponding parts, right? And we'll cross multiply. So 63 times 42 is a huge number. Don't forget to use your calculator. And then we have to distribute the 49, right? 49 times 8 is 392x. And 49 times 2 is 98. Okay, we're going to add 98 to both sides. 2646 plus 98. And then divide by 392. And I got 7. That's insane. They're both 7. I did not plan that. All right, so I will see you guys in class on Wednesday. I did want to share, because we are not having a regular class on Wednesday, you're going to have a play pause it on Monday. It'll be very short, sort of to take the place of that Wednesday class, and then you'll have a play pause it on Thursday. Again, these two are going to be very short. I feel like today's was not so bad, like just about 40 minutes. Some of it was me just chatting. So hopefully you're finding it's not too much, and we're getting some good practice in and some good direct instruction for you on the material. So I look forward to seeing you guys next week. Please reach out with any questions that you have. Bye, everybody.